in 2009, a perfectly functioning wind turbine just suddenly began to vibrate. And within seconds, the 75-ton rotor completely tore itself apart.
Wow. Just seconds?
Literally seconds, yeah. And it wasn't because of a storm or an earthquake. It was because the machine's own motion fed a catastrophic feedback loop.
Right.
Welcome to The Debate. Today we're examining the ME 503 study materials kindly shared by Dr. Chandan Chattaraj. We're looking at a huge central question for undergrad mechanical engineering students. Is rigorous theoretical vibration study a necessary foundational core subject?
Or, conversely, do these academic models just sort of fail to capture the chaotic reality of industrial design?
Exactly. And I strongly believe that understanding basic mass spring systems, single and multi-degree of freedom models, that is a non-negotiable prerequisite to preventing catastrophic engineering failures.
Well, I come at it from a different way. I mean, the textbook models we teach, clean, undamped linear systems or simple pendulums, they severely oversimplify how industrial machinery actually fails.
I see why you'd think that. But vibration is literally just the fluctuation of motion with respect to a stable equilibrium position, right? If you don't account for that basic math, you get severe machine damage, high power consumption, poor accuracy in things like lathes or mills.
Sure. But out in the field, future engineers aren't facing perfectly swinging pendulums. They are facing infinite degree of freedom elastic bodies where parts just break unpredictably.
Unpredictably? I mean, look at a simple shaft and disc. You have to understand fundamental torsional stiffness and damping, like viscous, material, or magnetic damping, to even diagnose a failure.
I'm sorry, but I just don't buy that. Let me tell you why. Real parts in heavy industry rarely break because of a simple, predictable external harmonic. They break from self-excited vibrations.
Wait, like the wind turbine?
Exactly like the turbine. Or think about a centrifuge dealing with anisotropic mass properties. If the mass is even slightly asymmetrical, it creates a minor wobble.
Right, which shifts the center of gravity.
Yes, which exponentially increases the centrifugal force, which in turn violently amplifies the wobble. The alternating force destroying the machine is created by the motion itself. A textbook linear model just doesn't prepare a student to analyze that self-feeding loop.
I concede that a centrifuge failure is incredibly complex, but how exactly do you propose an engineer fix it without theoretical damping models? To break that feedback loop, you need to introduce dissipation.
Well, you need to recognize the dynamic reality first.
Sure, but take magnetic damping. You have to understand the underlying physics. How a conductive disk moving through a magnetic field induces electrical eddy currents.
Okay, yes.
And those currents create a magnetic drag that converts kinetic energy directly into heat, completely independent of fluid viscosity or friction. You cannot design that braking mechanism without the foundational math of linear systems.
Yeah, but assuming you're just dealing with predictable periodic harmonic motions is a trap. In reality, an engineer is staring at entirely chaotic aperiodic noise on the factory floor.
But distinguishing between those states is precisely why theoretical study is so crucial. Actually, let's do a quick rapid-fire round for the students listening. How would you classify different practical vibration types?
Oh, okay. Well, you quickly contrast harmonic or periodic motions against that chaotic aperiodic noise I just mentioned.
Right. And it's not all hazards, is it? Because we deliberately harness beneficial vibrations, like in therapeutic platforms, electrodynamic shakers, or vibratory conveyors.
True, but you contrast those with the hazards like structural fatigue or passenger discomfort in vehicles. The diagnostic challenge isn't calculating a simple damping coefficient, it's distinguishing structural noise from a critical hazard.
And the line between a conveyor belt operating at peak efficiency and a resonant failure that shakes a factory to pieces is incredibly thin. You only recognize that threshold by mastering the theoretical limits of forced vibration.
Recognizing the threshold is important, I'll grant you that, but practical failure analysis requires a totally different paradigm. You have to interrogate the machine dynamically.
How so?
Well, for instance, if you cut the power and the alternating force immediately vanishes, even as the structure settles, you are dealing with a self-excited system. The rules of forced vibration, where an alternating force persists independent of the motion, they no longer apply.
Which actually brings us to a perfect quick quiz for the undergrad listeners to wrap this up. Ready?
Oh, lay it on them.
If an alternating force persists completely independent of the vibratory motion, is it forced or self-excited vibration?
A classic ME 503 question. The answer is forced vibration.
Exactly. Because you only know you are dealing with a nonlinear, self-excited anomaly by systematically ruling out forced vibration, using those exact textbook principles.
Provided you remember that the textbook blueprint is only the beginning. The real engineering happens when the machine introduces forces the blueprint never even anticipated. Troubleshooting means recognizing that textbook rules have hard limits.
And that is exactly why mastering the theoretical baseline is so vital. You have to understand the fundamental laws of physics before you can tame the chaos. To all the mechanical engineering graduates listening, deeply learning and analyzing these problems is how you'll build safer, more efficient technologies in your future careers. Thanks for joining us on The Debate.